45 minutes, and then, you know, stick around for questions. Okay, so the problem, let's see, the problem that we're facing when we're talking, I'm going to be talking about complexity in the atmosphere, and right away we can see that it has complexity. One of the, the obvious signs of complexity is that it has structures over a huge range of scales. And in this one picture here, you can see essentially, well, maybe less than a millimeter. The dissipation scale, typical dissipation scale of the turbulence in the atmosphere is actually about 0.1 millimeters. But in this smoke, the smoke picture here, you can see that there are some structures that are that small. Looking out the window, this is from the roof of the physics building, you can see structures in this picture here. They go from a couple of meters to maybe 10 kilometers or so, left to right. And then in a satellite picture, yeah, unless you're an astronaut, you couldn't see this directly, but on the internet, it's easy enough. This is an infrared picture at resolution of 4 kilometers, and you can see structures essentially going to the size of the planet. So we have over 1 billion in the ranges of scales. And of course, in time, if you go back to the formation of the Earth 4.5 billion years ago, and you go down to times of milliseconds, you will find variations in temperature, wind, or whatever. So there's a range of more like 1 billion in time. And of course, time and space are linked. Okay, so what I want to talk about is the idea of taming the details. So we're faced with this huge number of degrees of freedom. Actually, if you think of every cubic millimeter in the atmosphere as being a degrees of freedom, which is more or less true, okay, more or less can be quantified with scaling and multifractals actually, but to a good approximation, or depending on your criterion for activity, we have about 10 to the 27 degrees of freedom. So it's comparable to the number of degrees of freedom in a macroscopic body, your cup of coffee, for instance, right? Say Avogadro's number. So one of the ways that we could try to tame the complexity, to reduce it to something simpler, is to use the physical laws at the correct level. What do I mean by that? Here I have a picture. This is, okay, on the left, it's actually a classical picture of molecules in a box. Of course, a more realistic picture would be, quantum picture, but the consequence would be the same, because you could either go classically from classical F equals ma, apply it to a large number of molecules, and you get classical statistical mechanics, or you could do it more appropriately, quantum mechanics and quantum statistical mechanics. But the basic point I'm trying to make is that if your goal is to model a vortex in the atmosphere, for instance, a fluid, then in fact, almost all of those details are irrelevant. So how is it that we can make good, say, weather predictions? Well, it's because using thermodynamics and continuum mechanics, we just keep the relevant details, temperature, velocity, density, a few relevant variables, and we throw away all the useless information about positions of individual particles. Okay, so that's the reason it's successful. It can tame the complexity in this way, make it simple. But so in this view, you have micro complexity goes to macro simplicity. Okay. One of the points here is that you've gone from a stochastic description, say statistical mechanics, quantum mechanics, to a deterministic one, which is thermodynamics and continuum mechanics. Okay. But of course, as I mentioned, this hierarchy continues, right? So for weather forecasting or modeling the atmosphere more generally, we're not just interested in one vortex, one eddy, right? And we're not even just interested in a small number. We're actually interested in a huge number. So this is still actually a computer simulation up here, sometimes called the spaghetti picture of fully developed turbulence. And so you can see these are these gray shaded things are actually vortices. And you can imagine that we have absolutely massive numbers of vortices in the atmosphere. So what we want to do is say, okay, what are the irrelevant and what are the relevant aspects of this picture here? From the point of view of fluid mechanics, it's more or less the high Reynolds number limit, right? Okay, so the thing is that up until now, the idea of just chasing the details, if you like, has been quite successful, at least for weather prediction and even for climate modeling to some extent. So if we look at the history of numerical weather prediction, well, we have the first what you might consider global climate models back in 1979. I'll come back to that in a moment. And at that time, you know, computer power was something of the order of 10 to the 7 flops. Spatial resolutions were something like 500 kilometers, vertical level. These were state of the art at that time. Since then, you know, we've increased computer power by, you know, 10 to the 10, 10 to the 11. The algorithms, not a negligible improvement. This is an estimate by Peter Lynch that they're about 1 million times more efficient now than they were back then. Spatial resolutions, of course, have gone up, vertical levels have gone up, and also we've added multiple realizations. So everything has gotten, you know, much more details, degrees of freedom. But when it comes to one of the parameters, which is actually very important for humanity, which is the equilibrium climate sensitivity, right? That's how much warming we're going to get on average over the planet if we double CO2. That number hasn't moved, right? In 1979, the US National Academy of Sciences estimated that we would get between 1.5 and 4.5 degrees of warming if we double CO2. So that's actually a range of a factor of 3, which is really too big for, I mean, I called this, in my book, I called this a looming uncertainty crisis, because range of 3, if you don't, you know, if you're trying to make policy and you say, I'll do so much mitigation, and if I do that, then I will get only this amount of warming instead of that amount. Well, if the uncertainties are these large, then there's a kind of a decoupling between policies and consequences. So this number hasn't changed. It might change a tiny bit in the AR6 that's going to come out. IPCC, if a 6th assessment report that will come out next year. But at the moment, this has been the range over, in fact, 40 years. And so how are we supposed, what's the future look like? How are we supposed to do better? Well, according to the community, we've got in 2030, they're saying that we will, you know, so in 2030, this is the view that was first expressed by, well, there's about 20 authors here, including Tim Palmer, in this paper in 2010, where they asked about how they thought that the climate would be modeled in 2030, and their answer was, we need to be cloud resolving. So we need to go down to 2 kilometer. Well, they were hoping 1 kilometer scales. I think it's more realistic that we might be able to get down to 2 kilometer scales, but in any case, the point is that the lifetimes of these structures is measured in minutes, 30 minutes, maybe less, in fact. And then if your goal is to make a better decadal climate projection, then what you do is you average this over a factor of about 100,000 in time scale. And so essentially, it's an admission that almost all the details that you're using the world's best supercomputers to calculate are irrelevant, essentially, right? That's why you average them out, and you hope that the result will be accurate. So that's going down what I think is really a rabbit hole of chasing the details. Okay, so what's the alternative? So we want to think of high-level laws that, in this case, in fact, will be stochastic laws. And so how can we think about those? So one of the first choices we have to make is, are these approaches going to be scale-bound or scaling? What do I mean by that? Scale-bound it's actually a term coined by Mandelbrot back in 1980, but, and I have here attributed it to very appropriately a Dutch scientist, Van Leeuwenhoek, who's been attributed, well, he didn't invent the microscope, he invented the first powerful microscope, and there's no doubt that he was the first one to discover what he called a new world in a drop of water. So essentially he discovered microorganisms somewhere around the end of the 17th century. And so it's this idea that every time we blow things up by a factor of 10 or so, that we discover something new, that every range of scales, something new goes on that we have to eventually model and come up with a mechanism. That's been strongly in our thinking ever since then. And it influenced already, this was really the first modern schematization of how the atmosphere works by Murray Mitchell at the mid-70s. And at this point, we were just getting the first, paleoclimate data, say ice cores. And so we were just starting to really be able to quantify some of the longer periods of climate in the past. And so Mitchell called this a guess, an educated guess in his paper. So he was very modest because he realized the data at that time was most of it was quite primitive. But you can see that roughly the idea is, he's got from an hour to more or less the age of the Earth here. So he's a spectrum, and he's basically saying that you've got essentially a white noise background, or possibly linear rise regimes followed by white noise. So those would be actually Ornstein-Uhlenbeck processes, integrals of white noise, in fact. But most of the things that you're supposed to pay attention to are bumps. You have a daily spike, in fact, for the diurnal cycle, annual cycle. You've got ENSO events, you've got Milankovitch cycles over here, and et cetera. So, but the idea was that you have a boring background, which is this continuum that it was more or less white noise and uninteresting, and you have a few specific scales that are important. And this, 40 years later, this was kind of ossified and turned into a kind of almost an official doctrine, for instance, by the National Oceanographic and Atmospheric Administration on their paleoclimate website. They took this, they said this was inspired by Mitchell, and they reduced his guess into just a schematic like this, where now they just have increasing variance, so they don't claim actually this is a spectrum, but you get the idea that there's this totally uninteresting background. So that's this scale-bound view that you have to think in terms of factors of 2 or 10 in scale only. But in fact, when you actually look at the real, before I get to the real world, let me just mention the kind of opposite extreme, and the reality is going to be somewhere in between there. But you can see that you've got Mandelbrot here zooming into the Mandelbrot set, blowing up, and you can see you blow up, and you get something not too different at some level of magnification. So you have the possibility you blow up and you don't actually get anything new. Okay, so that's the opposite scaling view. And when you compare Mitchell's view to the actual data, so here I've had to use real instrument data down here to say century scales, and then various paleo data taking me to hundreds of millions of years, in fact. But you can see that there, and I've drawn this log plot, so I've drawn straight lines that suggest that these could be modeled by power laws, which means scaling. And you can see that actually Mitchell's view was wrong by a factor of about a quadrillion, 10 to the 15, right? So really, Mitchell has to be turned on his head in the sense that almost all the variance actually is in the background. Doesn't mean that this is a real diurnal spike, a real annual spike, and there's really something happening at Milankovitch scales. It's not a sharp spike, although this is obliquity spike that you can see from something like 2.5 million to 800,000 years ago. But in the last 800,000 years, which is this paleo data here in red, it's not, you know, it's a broad, it's a peak, but almost all the variance is in that, and not in the spikes. So, you know, to focus on just spikes and things is actually focusing on it. You know, you're not looking at where the main variability is. And so the thing is, I think we have to understand the scaling, not exclusive to the spikes, but certainly we shouldn't keep ignoring what was considered the background. Okay, another way of looking at that, which is maybe more easy to understand, is instead of looking in Fourier space to look in real space. This is what I'm calling fluctuation analysis. Actually, it's just based on Haar wavelets going back to 1910. But with these fluctuations, you can actually see, you know, it's more or less the same data as before. Most of it's the same data as before. You can see a regime going up to about 10 days, which is roughly, so temperature fluctuations. These are actually root mean square. They increase, tend to increase up to about 10 days. 10 days to 30 years or so, they tend to decrease. So you seem to be converging to a climate state. But then just as you think you're converging, then the fluctuations start to increase again, and you end up, this is, say, ice ages. So these are paleo data over here. And exactly what's happening here depends on, in fact, our current epoch, the thing is going up again because of anthropogenic warming. But you can see roughly these scaling regimes here. And I'm just going to be interested in these three: weather, macro weather, and climate. These very low frequency regimes, we don't really have a lot of information about them. This is all based on benthic paleo data. But the spikes, for instance, the maximum, the highest variability is essentially around 10 days, which is the lifetime of planetary structures. It's also the deterministic predictability limit for atmospheric models, right, due to sensitive dependence, initial conditions, chaos. And also you have, this is essentially astronomical, but I put plus question mark because there are many questions about how the astronomy really couples to the atmosphere. So this is still definitely lots of unanswered questions there. And this point here where we make a transition from fluctuations seeming to converge to a climate, a well-defined climate. We average more and more our anomalies, and we get convergence. But in fact, at some point, the point to which we seem to be converging starts itself to move. And in the industrial epoch, that's around 15 to 20 years at the moment due to anthropogenic change. The response to anthropogenic forcing exceeds the internal variability, if you like, after about 15 to 20 years at the moment. But even before, in pre-industrial, after a couple of centuries, for timescales longer than a couple of centuries, then you also had an increase. Okay, so another way of looking at the same thing. So if we're looking at these methods that take advantage of scaling, first we want to, so I've given that evidence for scaling in time, but in fact, the reason that it's plausible is because there's scaling in space. And the scaling in space was essentially the basis for laws of atmospheric turbulence that initiated not only, but most importantly by Richardson in the 1920s. And of course, Kolmogorov. These are just a small fraction of what I'm calling the pioneers of turbulence. And the point is that they all believed that that essentially the statistics of these high Reynolds number systems, or including the atmosphere, the statistics of fluctuations behave something like the fluctuations were equal to some turbulent flux times a scale to some power. Okay, and the fluctuations were really considered the difference, say, in temperature between one point and another in your fluid. The turbulent flux was considered to be more or less uniform, quasi-Gaussian, and scale, the idea of scale was just a usual isotropic notion, the distance between 2 points. But what's happened since the 1980s. This is part of the nonlinear revolution, specifically the nonlinear geo part of the revolution. Is that the notion of fluctuations has been greatly generalized thanks to wavelets. So there's a whole mathematical theory that allows you to define wavelets in an infinite number of ways, the fluctuations in an infinite number of ways. The turbulent fluxes, it's now clear that they're highly intermittent. I'll show you some data on that in a moment, but they are essentially multifractal, and as a result of cascade processes. So that mathematics took a while to congeal, but it's fairly clear now. And also the other key point is that the notion of scale can't be isotropic. In fact, the isotropic Kolmogorov law never, in fact, seems to hold in the atmosphere. It holds extremely well, however, in the horizontal, but it's actually an anisotropic law, and you always get something rather different in the vertical, closer to, in fact, a law by Bolgiano and Abukov that I won't have time to discuss, but okay. So this is just some rapid collection of data from satellites. This is a global scale at the lowest wave numbers. So you have visible, thermal infrared, different infrared. You've got passive microwave, aircraft trajectories. You have reanalyses. Okay, so you have all these different fields, really up to planetary scales, with maybe after 5,000 kilometers or so, you can have deviations. But over a huge range of scales, you have excellent power laws. These are log-log plots. And in fact, even you can compare our planet to Mars, and you get almost the same exponents even for the same. It's quite impressive. Okay, so one last thing is this multifractality. As I mentioned, if you took weather data at 1 hour, say this is Montreal here, 360 consecutive hours, I removed the daily cycle, and you can just look at the absolute differences in the temperature. And if you normalize them by the average of the absolute difference, then you get something like this. And you can see what I've done is I put this thick black line here, or solid black line. That would be the line that you would get. You would expect the maximum of those fluctuations, those differences, absolute differences. That would be the maximum if the process was Gaussian. So it would correspond to a probability of 1 out of 360 for a Gaussian process. And what you see is you frequently get values they exceed it much. So this dashed line here would be 1 in 10 to the 9, for instance. So, these are very, very far from being Gaussian. Climate, I'm thinking here, this is 240-year resolution from paleo data. Well, it's not really Gaussian, but it's not as extreme as weather. But this macro weather regime, this is data actually at 4 months, actually is almost Gaussian, remarkably enough. You can do the same thing in space. And in space, you find so you do variations, in this case, aircraft data every 280 meters, or 1 month data, 1 degree in space, and okay, these different time scales. But you see, again, these huge, huge fluctuations that have nothing to do with Gaussian. Turns out that these huge fluctuations in either time or space imply, in fact, spurious spikes in the spectra that can easily be misinterpreted as more or less periodic regimes if you use Fourier analysis coupled with the usual null hypothesis for detecting spikes in Fourier space. But I don't have time to go into that. So this is the quasi-Gaussian exception, the macro weather, that we'll come back to later. And the way the multifractal approach to this works is you define each spike corresponds to a certain singularity. Lambda is the range of scales, say 360 here. And then you get a scale invariant probability distribution characterized by this codimension function. And I don't have time to go into that, but okay. So these are just some of the generic properties of multifractal processes that are important in the weather regime. Okay, you get another interesting thing is you generically get power law extremes, which sometimes have been called of black swans. And again, I don't have time to go into any of that, but we'll discuss that later. One thing relevant for complexity studies is that the fact that this horizontal version of the Kolmogorov law, in fact, seems to hold over pretty much the whole range in the horizontal. And it fundamentally involves this energy rate density here. In turbulence, it's the rate that energy cascades from large to small scales. This quantity was actually proposed in 2003 by Eric Chaisson as a metric of cosmic complexity. And so, for instance, he goes through the cosmic evolution, basically, from an astrophysical point of view, but he takes it all the way to society. He tries to estimate epsilon for all kinds of different systems. But the thing is, this quantity just happens to be the main quantity in the horizontal in both, in fact, Earth and Mars that sit in here somewhere. Okay, so at the moment, these alternative approaches for predicting the weather, essentially stochastic approaches based on scaling and multifractality, have not been able to in any way compete with the usual numerical weather prediction approach, chasing the details. But what about these longer timescales, macroweather and climate, especially macroweather, where I've shown indications that at least in time, it may be quasi-Gaussian. Okay, so why do we need these? Just to remind you, the problem is at the moment, if we try and extend the weather models to the climate scales, the way it's usually done, you end up with these huge models and each model, the problem is it has its own climate. So then you take 32 different GCMs, say, and you do what they call the multi-model mean, and you hope that the mean of all these different models is close to reality, but the thing is each model has its own climate. So what you really want is to make a model which is based on the real world climate, basically huge amounts of past data ultimately. So you're kind of forcing your projection or prediction into the real world this way. Okay, so one proposal that I think is particularly promising is based on energy balance principles. And in particular, the discovery that this ancient equation, which is just a heat equation, right, for continuity, temperature, it's the only slight difference is I've made different vertical and horizontal diffusivities, but it's basically just a continuum heat equation. And so if you apply this to kind of the average state of the atmosphere at 1 month scales, at maybe tens or hundreds of kilometers in space, so you're averaging over a huge number of degrees of freedom, the weather degrees of freedom. The basic idea goes back to Bedico and Sellers in 1969 and was applied very successfully, but using a two-dimensional version of this. And ultimately, they got latitudinal variations of the Earth's temperature. So what is new is that we found that if you put back the vertical coordinate, you can then apply the correct radiative conductive boundary conditions. So the forcing for this then is fluctuations in solar output. It's anthropogenic, greenhouse gases, volcanoes. These are forcings for anomalous temperature changes. Some of those watts per square meter end up increasing the temperature and hence black body radiation to outer space. This is the linearized version over here, but some of it also gets conducted into the subsurface where it is stored and can come back quite later. So the new thing is that this leads to what's called the half-order energy balance equation. So if you just want the surface temperature Ts, then you get it directly, but the time derivative is of half order in this case. And the thing is that this is 100% classical. In fact, basically the connection between the classical heat equation and half-order derivatives has been known really since the 1960s, especially since the 1980s, but nobody has applied these specific boundary conditions to it. And also there's a specific technique called Babenko's method that allows you to in fact generalize this. I won't have time to go into it, but the point is that in fact, you get these this implies long memory, these half-order derivatives. So heat that you put in a long time ago by excess forcing 50 years ago, say the surface of the Earth somewhere, that can come out now and affect your temperature predictions and forecasts. And so if we're thinking of this in terms of usual energy balance, here's a what's called it's a box slab model, standard energy balance equation with first order derivatives. And this is just saying that if you force, the Earth is just treated as a huge slab of material, and energy just gets stored in usual thermodynamic degrees of freedom by heating up, okay? And it has a relaxation time, which just tells you, says ultimately the Green's function of this is exponential, right? So if you wanted the solution, you just take a convolution with the Green's function, which is essentially an exponential. Here I've done it for the step Green's function, but usually use the impulse Green's function, Dirac. But here you can think of this as generalizing. So the half order would be h is a half, but more generally you can get h is a fraction between 0 and 1, and you have the fractional energy balance equation. Here's just your definition of a fractional derivative in terms of convolutions. And so here you get, instead of exponentials for your Green's functions, you get generalized exponentials. And in fact, in this case, you have both a high frequency power law regime and a low frequency power law regime. And well, we'll see those give, one gives climate projections and one gives monthly and seasonal forecasts. Okay, so how can we use this to project the climate to 2100, for example? So this is work done with my student Roman Project. It's currently under review, actually. But the point is that he used global temperature series going back to 1880. He used these are the different IPCC fifth assessment report representative carbon pathway. So these are scenarios to 2100. He's looked at some of the new CMIP6 ones also that are starting to come out now. But in any case, he gets this H parameter is not far from the half value. It's actually, the median is like 0.37. And he gets this climate sensitivity of about 2.46, but plus or minus about 20.25. So that's right in its full agreement then with the IPCC value. Remember, that was 3 plus or minus 1.5, or this range 1.5 to 4.5. So we're completely in agreement, a little lower for the median, but still complete agreement. If you look at the behind projections, here we have the real data, 5 different estimates of the past data in red with their 90% confidence interval. The GCMs, 32 GCMs used in the fifth assessment report, are in gray, with their multi-model mean being the middle gray value. And you can see the FEBE estimates, 90% confidence limits, are the blue. And so first of all, we're in total agreement with the CMIP5 because our limits, 90% confidence limits, overlap. But we're actually quite a bit more accurate over, for instance, the pause, where the GCMs were in fact a little high. Okay, so this is this famous pause 1998 to 2015. So we were right in there. About 10% of the temperatures were outside, as they should be, since this is a 90% confidence limit. Okay, so how does that work when we go to the future? So we put in the 4.5 scenario, which is moderate mitigation. And you can see, once again, up to 2100, we have essentially full agreement with the GCMs, but again, a little on the low side, and with about half the uncertainty. So we're going a long way to getting to solving this, or avoiding the looming uncertainty crisis that I mentioned. And I should mention, this is the first time that there's really an alternative to the GCMs for making these projections. And so we know that in science, if there's only one method of getting a result, then one can be skeptical of the result. But when two totally different methods give the same answer, then one ends up with much more confidence in both. And so we regard this as, on the one hand, a vindication of the GCMs, and the GCMs are also vindicating our approach. The last comment on this is that you can apply this technique to each GCM. So as you can work out the age parameters and the sensitivity to each GCM using its past, comparing it with data. And so we can then project using the fractional energy balance equation, the GCMs. And we find actually that we can, the orange is the projection of the GCMs, remove the uncertainty bounds just to make this more obvious, and the black is the actual multi-model mean. So in other words, using our technique, we can almost perfectly project the GCMs into the future. So that's why we think if we use the data to project into the future, we can be more confident. And then there's a so-called hybrid method, which tries to take advantage of GCMs and our method to get even better results. Anyway, we could discuss that later. Last thing I want to mention, I'm nearly done, is the application to high frequencies, where that means monthly, seasonal, and maybe annual forecasts. This is work in collaboration with Lenin, Del Rio, Amador, and it's evolved into this forecast package called StochSIPS, the Stochastic Seasonal Interannual Prediction System. And so this is based on the high frequency part of the Green's function. Okay, so we can forecast, say, global temperatures this way. So here, what I've shown is this is the amount of lead time. Here I have the skill in the vertical axis. StochSIPS then for what, this would be 1 month ahead, in fact, forecast. This is your skill level, and you can see the skill goes below 0 at between 3 and 4 months. So 0 is just climatology, but it turns out that CanSIPS, which is the Canadian GCM-based model with 20 members, actually does quite a bit worse. A lot of that is because it doesn't get the annual cycle so well. But an interesting point is that if you combine the GCM-based forecast with StochSIPS, actually you can do better than both. Okay, that's this CanStoch hybrid. So some interesting potential there. But what about regional forecasting? Right, so that was just for the global average temperature. So if we apply the same technique just by forecasting each pixel from its own past, well, that's, so how could we even justify that? Because we have the idea that different spatial locations have information that can be useful for forecasting. Remember that, of course, GCMs are an initial value problem, so they use no past, they just use the values of the fields at t equals 0, and then, but they try to get all the fields they can for t equals 0, and then use the spatial information to integrate forward the equations. In this model, basically we have white noise forcing called the innovations. They are convolved with a weight, which actually, this k function, which is actually a power law. So it has a long memory. And so the ith pixel depends on the innovations of the jth pixel weighted over time by this kernel. And then you're summing over the influence of all the different pixels. The key point is that the innovations which are generating the whole thing, white noises, that these are delta correlated in time. So that, yes, you can have strong correlations in the innovations at different locations corresponding to highly correlated physics. But these are white noises, though, that they're, are not time correlated. And so when you do that, you get, let's see if this works, right? You get this simulation. So you can use this to make a simulation. And on the left, I have the actual monthly temperature anomalies at 2 meters above the surface from the NCEP reanalysis. And since 1968 here, the data goes back to 48. The simulations are essentially, they're not supposed to be identical left and right. They're just supposed to have identical statistics, including El Niños that appear and disappear and stuff like that. I won't have time to show the whole thing, but okay. Well, you can get the idea. If we actually look at the El Niños, because this is sort of the one of the things that GCMer will look at whether if he makes a change or improves them, has a new model, he will like to see how well it reproduces the El Niños. So this is a temperature-based El Niño index, the ONI. This is the real data down here. And you can see these are just 3 simulations. So these are a kind of an emergent index from this stochastic model. And you can see actually it works quite well. You can use then the same model to do these forecasts. So here's CANSIPS 1 month ahead, and then StochSIPS. Blue is when you're doing worse than climatology, actually. Red is better than climatology. You can see that the GCM at 1 month does a bit better over oceans, but worse over land. But you can put the two together in CanStock and you do better everywhere. And this just shows the amount of improvement with this sort of hybrid approach. Anyway, okay, so this raises the question, can we use data from other locations to improve our forecast? Because these are based purely on just taking long time series at a single point and exploiting this very, very long memory. So can we use, for instance, teleconnections? So teleconnections, have been, it's this idea that there are these links between points far apart. One of the pioneers, Tsonis, 2006, published this paper. Here he shows pressure anomalies at 500 millibars. The idea is you say that 2 different pixels on the globe are linked, in fact, in a network sense, if the correlation between, the time series at those 2 points are correlated to greater than some threshold. And then the color here shows you a given pixel, how many other pixels in the world is this connected to in that sense? And red, in this case, it means something like 50%. Very high connectivity over the points in the equator. If you do the same for temperatures, you get something like this. Okay, so high correlation, correlated with many, many points red and less yellow. So the question is, can these teleconnections help us, say, the temperatures over the Pacific, El Nino, for instance, can they help us improve the prediction in Montreal? Okay, so to answer that, though, we really need to look at the notion of Granger causality. That's the technical thing. So Granger causality, so 2 points are linked in the Granger causal sense if the information, say at pixel J, can be used to improve the prediction at point I, pixel I. And if the error in the predictor has no correlation with so this is the error in the future prediction based on a predictor Ti at pixel I, times in the future. If that has some correlation with the past data at a different pixel, if there's correlation, then you have Granger causality. And if you have 0 correlation, then there's no causality. And in fact, what this is showing is that at time t equals 0, this is the temperature correlations, this is the innovation correlations. Yes, there are teleconnections in the innovations. They're not as strong as the temperatures, but you have them. But as soon as you go to 1 month or 3 months, then essentially there is no correlations in the innovations. So essentially what this is, and there's still strong correlations in the temperatures. So what this is showing is that teleconnections have absolutely no Granger causality. So they are very misleading if you want to use those teleconnections to try and improve your forecast. So alternatively, if you have a sufficiently long time series at some pixel, then adding information from other locations will not help you. Okay, so now as I'm going to my conclusions, probably already a minute or 2 over time, but what I've tried to do today is to approach complexity by trying to tame the details. There are other approaches to complexity, as I'm sure you're all aware. So that's this idea that there are low-level laws which may, in fact, have many details and be complex because of that. And what we should be aiming at in the case of the atmosphere is higher-level laws, which can be simple because they essentially ignore irrelevant details. And one of the ways of handling the details is using scaling. So the classical approach to weather models is essentially chasing the details. Macroweather and climate, you essentially expand those into, you have a GCM and you add an ocean model, a cryosphere model, a carbon cycle model. So you chase the details more and more. That's what we're presented with as the future. On the other hand, higher level stochastic turbulence-based approaches at the moment have not led to improved weather forecasts, but we are arguing that symmetry-based approaches that are using scaling and energy conservation or energy balance is a good basis already for macroweather and climate, at least for some of the fields such as temperature, and that these are already interesting alternatives, even though they have barely been developed. So thank you. That's all I wanted to say today.
Okay, thank you very much, Shaun. You can also electronically clap, but so yeah, I see already some points raised for discussion in the chat, and everybody has now sort of opportunity to do that. You can also mention in the chat, that you just have a question, and I will give you a turn, and then you don't have to phrase it into the chat box. So Jaap Mont has raised already several points. Jaap, do you want to ask questions? I don't hear anything. You're still muted, Jaap.
I think I did. Can you hear me now?
Yeah, I can hear you now. Yeah.
Okay. Well, I was wondering, in terms of computing power, we are going to get quantum computer power. Would that be quite helpful?
Well, I mean, at some level, you could say, let's say that your quantum computer could calculate the position and velocity of all of the molecules in your cup of coffee. And what you really wanted to know is the coffee at the right temperature to drink, right? And so somebody says, here, I've got this quantum computer and I have all these positions and velocities. The trouble is that what you really need is some way of, separating out the relevant and the irrelevant details. So, I have nothing against quantum computing, but I think at some point, we're going down a path which is, is not optimal, especially since we already have this history that with these GCMs, which are already huge, that they end up having each their own climate. And just putting more and more details in there, I think is not going to alter that aspect.
Okay, I'll come back with another question maybe later on. So somebody else now, maybe.
Yeah, Deb has a few questions. Deb, go ahead.
Let me unmute first. Yeah, I think, so you have this exponent h in one of your time-delayed differential equations. I suspect that is the Hurst exponent.
Okay, well, it's actually not it's a fractional differential equation.
Yeah, I was wondering about the h notation that reminded me of Hurst exponent, and my main question is, question was that how do you get that value? Is it is it from one of your plots earlier you had shown during the talk?
Okay, well, the way, first of all, it's Hurst inspired exponent.
Right.
So let's see here. I've got, so you can see this equation actually has a high frequency and a low frequency limit. And the way we actually got this was we first looked at high frequencies, and at high frequencies, this is essentially fractional Gaussian noise. So you can get it's related to it. You have to subtract a half to get the exponent.
Yeah.
Fractional Gaussian noise, and at low frequency, it's yet another exponent. You can see the sign of h is changed in these two things. And we made climate projections based on estimating the exponent in this low frequency Green's function, and then we did these forecasts using H in this function, and then all of a sudden we realized that they could be connected so they were different exponents, but they were exactly the difference expected if we use this equation with a single exponent. So that's actually how we came to the FEBE. And then we realized that this classical continuum mechanics heat equation actually already gives you this half order version, which is very close to what we observed. So that was actually the historical order. So we didn't start by saying, let's look at energy balance and then do, I'm telling you the way you can look at it now, but the way we actually found it was we thought these were totally different beasts when we, the high frequency exponents needed for these fractional Gaussian noise models, and then the low frequencies needed for these climate projections, but actually they are quite related to each other. And so, the climate projections that I'm showing you here, this is based on a Bayesian analysis of past data that allows you to narrow this range down quite a bit. Yeah.
So more goes into it than meets the eye, let's say. I had missed the detail.
Well,
so yeah, do I have space or time to ask another question, Hank? Or, yeah, so I'm actually coming from a very materials background, and there in materials we have also, let's say these are mesoscopic to macroscopic size materials, so we have many atoms there, and one advantage is that at least the models that there are all these processes that are taking place at different scales at different times across many decades. These processes can be linked to each other, and these are, of course, there are models, and no model is perfect, but at least is there. And there you actually do see, I mean, you can almost derive from the very first principle because of these coupling of different processes that are running with each other. You can derive these exponents and derive these power laws and so on. And Hank recently, sometime before the summer, he sent me a paper where all these timescales were mentioned. But I guess one of the things that I always miss is kind of the causal connection, or causal connection is probably too general term, but I mean how the processes are linked with respect to each other. That might actually give a clue about how to let's say derive this or write down an effective model which can reproduce some of these observed power laws. I mean, I'm always very intrigued, personally very intrigued by these exponents, and in the context of materials you can actually predict these exponents theoretically and compare to observations. Could you say it's so? I guess the main thing is that I'm missing the connection between how these different processes at different spaces, spatial and time scales are related to each other.
Okay, well, I mean, of course, the first
laws of climate, let's say.
There's a massive, of course, you're right that's what you would like to do, but that there's been a century of turbulence work, and actually there's still not really a consensus about the exponents in the weather regime. There's the famous Kolmogorov 1/3, and except it turns out the Kolmogorov law only holds in the horizontal but not the vertical, and that's still actually not well appreciated. Also, that there are these massive intermittency corrections to it, which was the whole 40 years of multifractal development. Yes, there is. So there's, in fact, almost all the exponents. In fact, Kolmogorov exponent is about the only one that has a kind of a fairly strong explanation. There are many turbulence theories, but the actual observed exponents and the exponents that come out of weather models tend to be unexplained for the moment. So they are just regarded. But the thing is, the model itself, right? Navier-Stokes equations, which all this is based on, have no scale over a huge range. They're scale free. So there's a, that's the physical basis, is a physical principle of scale invariance that the models respect. And so anyway, when you get to these longer scales, at the moment I'm just talking about the heat equation, and the heat equation with exponent 1/2 is actually 100% classical. It's just that with other boundary conditions, it's not so useful to introduce fractional derivatives, although it has been done for at least 40 or 50 years in specific cases. But with the specific radiative conductive boundary conditions we have, then it gives you something much more interesting. And there, the hope is that the system is relatively linear with respect to small anomalous forcings. And I should say that actually the GCMs seem to be very linear in terms of their response to at least the forcings that they have used in, say, IPCC projections. So we have papers on that where we look at that. But basically, the GCMs will project into the future the patterns of warming that they've seen in the past. And they do, so that's why we can reproduce the GCMs quite accurately, even though this is in fact just a linear model.
Yeah, that the fact that it's linear in forcing surprised me, but okay, I mean, I'm not an expert in weather or climate models. I'm not a climate scientist either. Okay, thank you.
Okay, any other questions? Jaap, do you still have some points I listed?
Yes, there was one view graph that showed that when you combine two methods, one was much better than the other, then the combination gave a much better result. So there must have been something missing in the better method. And what was that? Was it clear that the better method could be improved to give even a better result than the combination of the two?
Okay, well, this is, I think, is this the graph you were referring to?
Yes, right.
Right, so here what I've done is I put the, so this is for global, first of all, this is for global temperatures, globally average temperatures. And so the StochSIPS model is this pure stochastic model that exploits this very long memory in the system. The CANSIPS model is a traditional GCM with 20 members. It's the Canadian, it's for two different Canadian models. The output is operationally available since 2014, and we have Hindcasts back to 1980. And of course, they're totally based on different. One is an initial value problem, whereas StochSIPS is essentially a past value problem. And so StochSIPS is quite close, actually, to the stochastic predictability limit. CANSIPS still, because it has an ocean component, the deterministic predictability limit of the ocean component is about 1 to 2 years. Of the atmospheric component, it's about 10 days. So when you're talking about these models at 1 month, 2 months, 3 months, you actually have some deterministic skill in there, still from the ocean component. And what we did to get CANSTOCH was we took, we made a linear, so we said, okay, we have the CANSIPS forecast for 1 month, 2 month, a year ahead of time. We have the StochSIPS forecast. They're based on totally different principles. And we combine them in an optimum manner, but just linearly. So nothing special, but we worked out the least mean squares linear combination that gave us the highest skill. We trained it 1980 to 2000, and then we verified it over the following 10 years. And so that's what's surprising, but it's less surprising when you realize that really you're exploiting rather different aspects. So a GCM is some kind of weird deterministic stochastic mixture when you go to 1 month and 1 season, right? Because the atmospheric component is way beyond the predictability limit, so it's essentially stochastic. But the ocean component is still in its deterministic regime, and so it still gives information. So anyway, so let's see, well, I have it here maybe. Okay, well, anyway, there's some slide that shows, okay, this is the slide. This shows that for 1 month ahead, you get higher skill from the GCMs over the ocean,
right,
but lower over land. And we're not doing that bad, but we're not as good over the ocean. We're a little better over land. And then we combine them and you get better everywhere. And this shows the difference between the hybrid model and just the GCM. So we get bigger improvement over land.
Okay, yeah, that makes it clear. Thank you.
Okay, any other questions? I see nothing. I have a question to Shaun. I've like to ask you that for a long time already. I mean, if you look at backgrounds, right? I mean, you mentioned the background and looking at different scales. Then I always view the background as you take a certain process at a certain time scale, and then you look at, say, small scale processes, right, which can be considered as noise on that long time scale, and then you force that to the larger scales, and then you look at the behavior. So to give an example, Hasselmann's model, where you have a mixed layer ocean, you force it with atmospheric high frequency variability, and you get red noise. Now, in that sort of viewpoint, I would view, say, background. If you look at, for instance, say, very low frequencies in your mega climate regime, that would be sort of processes which are caused by ice sheets and carbon cycle, for instance, but mainly maybe ice sheets, ocean circulation. And those are forced by, well, higher frequency variability, right, which can be considered as noise on that particular time scale. Now, then the process giving you that power law will be you'd have to build a model which shows that the dynamics of that ice sheet will give rise to that particular behavior, right?
Yeah.
That is not turbulence. I mean, that's something very different than what you have in the atmosphere, where you understand that very well. I mean, is there any work into that direction to show, where this power law comes from by looking at the sort of real processes in the system?
Well, okay. Well, one, I mean, the quick answer is not really, but the thing is the fact that if you have radiative conductive forcing of the system, right? I mean, that's sun basically, right? You turn the sun off and game over, right? There's no climate, there's nothing. So the fundamental forcing of the whole system, involves in a generic way fractional derivatives. And as soon as you put fractional derivatives in, so we could then revisit, and this is something I'd like to do, is take these fractional energy balance equations and revisit some of these, ice sheet models and things of this nature, but put in a fractional derivative term in there, which would correspond to parts of the system which are involved in essentially radiative balance. So those parts of the system generically get this sort of long memory, which just simply has to do with the fact, it could be just classically energy going in, taking a long time to diffuse in, and then the forcing goes away, taking a long time to come out. And those will certainly broaden any spectral spikes that your model might generate. So, it would be quite interesting to look at, chaotic systems, in fact, but with fractional derivatives, and some work exists in the literature, not as far as I know applied to the climate, but fractional differential equations is a huge field now. And here we're talking about, I mean, the basic fractional differential equation is called the fractional relaxation equation, which is one of the simplest, but there's still not much been done when it's stochastically forced. And then I didn't discuss the spatial aspects of that, but there are spatial implications which also involve, in fact, you get fractional space-time operators ultimately that just come out totally classically from the continuum the heat equation.
Yeah, okay. But they basically model the memory, right, in the system.
So those automatically give you a long memory. Yeah.
Yeah. Okay. Okay, thanks. Any other final questions from the audience? I see nothing in the chat. And if not, I see nothing. Then I want to thank Shaun very much for sort of being up so early to give us this talk. Well, 9:30 wasn't too bad.
9:30 wasn't too bad.
I recently got an invitation for talks and being at 12 o'clock at night, or those kind of things. So this is not too bad. But thanks very much for giving this very nice talk. I think I hope that it stimulates people also in different fields to take this as material which can be useful, particularly also this fractional derivative models. I think that's something which might be also very useful in other areas. And so to close off, there will be a talk by Rudolf Hanel in October. It will be announced from Vienna, which is on a very different topic, but also related to scaling. And with it, I'll close here the session. Thank you very much for attending.